Hey there, today we'll be doing this question that is 958. Check completeness of a binary tree on Leetcode. Given and the question statement is given the root of a binary tree, determine if it is a complete binary tree. And the definition of a complete binary tree is that all the nodes of the levels are all filled except the last level, which is filled as left as possible. It can be empty also, but it has to be filled as left as possible. That means if we have something like 1, 2, 3, and let's just say this is my last level. If I want to fill a node, I want to fill another node, I cannot put it here. I have to put a node first of all on the left, then only I can put something on the right to me. Okay, that is what a complete binary tree means. And also the difference between any two levels cannot go beyond the leaf node, and other node cannot be greater than 1. That means if I have something like this, 1, 2, 3, if you see the difference between this and this is greater than 1. That is what we mean by that. Now how to do this problem? So all you need to do is you just have to know a simple BFS, and that is it. And let's just discuss the approach on how we are going to do this question at first. Fine. So if you understand these two cases, you'll be good to go, and you'll be able to code it by yourself also. So coming on to the first tree right here, I've drawn already. So at first, what do we do in BFS? We travel level wise, right? We travel like this. This is how we are traveling in BFS. So all you need to check a condition is that if I ever happen to find a null node, ever, okay, I can never have any nodes after it. That is what you need to check, and that is this whole question all about. And how is this actually true? We'll check into that. So at first in BFS, what happens? We travel level wise. So in our queue, what is there? One is there, done. Now one will say it has two children, that is 2 and 3. So what happens? I go to the next level. I will remove one from my queue. I will say 2 and 3 are my next children. Fine. Now 2 has how many children? That is 4 and a null. This is a null node, remember? So 2 travels and 2 gives us what? 4 and a null node, remember? Now we go on to the next part, that is 3. 3 has what? 3 has a 5, right? So this is my queue right now, that is 4 and a null node and 5. Now this part is very important. At first we'll go to 4. We'll see what are its children. It is null and null, so it doesn't matter. Let it be. Now then comes a null node. Remember what we discussed earlier? If a node is coming after null, then that means it is an invalid binary tree, complete binary tree. Okay, so there is a null, and after null there is a node indeed. So that means this is a invalid complete binary tree. This part is very important. Now why is this actually true? Because remember, complete binary tree means before filling any node on the right, I need to first fill this one. Then only we can go on to the right part. That is what a complete binary tree is. And that is why this whole checking of null before a node gives us the correct answer. So let's just understand this one, and then we'll be good to go for the code part as well. Okay, so at first we insert one into our queue, and then we process its children. That means we see what are its left and right children. So 2 and 3, well and good. Now we then we take on 2. 2 has how many children? That is 4 and 5. Let's insert it into our queue. Now we go on to 3. Now 3 says I do not have any children. So what are its children right now? It is null only. Okay, both are null, which is done. So let's just insert null twice. Okay, for now. Now 4 says I have a children. So 4 will say, okay, I'll insert 6 because it has a children. It goes after, right? Now 5 says it does not have any children. So let's just ignore this, and there is a null and null. Now we see there is a null. Okay, there is a null. Well and good. Null cannot have any children. We move on ahead. We just pop it out. There is a null. We will move ahead. Remember, after a null, if there is a node, which is a valid node, then it is not a complete binary tree. And that is it for this one. So all we have to do is we just we just have to make sure we just keep a check, that is keep a variable which will say that I have already found a null, you cannot have any nodes further on. So let's understand how we are going to do this in the code, and it will be good to go for. So this is a simple BFS that we do, a very simple one. All you need to understand is this found part, this check that we are writing. So this is a very easy BFS code that we write, the basic one. At first, we push it into our queue. After that, we iterate for till the queue is empty, and then we just iterate till whatever's in our queue right now. After that, what am I saying? I've taken a found variable. And what is this found saying? This found is saying if you have found null, make it true. This is the part where we are doing it. If you have found null, then make this variable to be true, and you just continue. Okay. Why continue? Because remember, a null node cannot have left and right children, right? It just has null only. So we will never do that. So that is why we have just put a continue statement here. Now, in a simple BFS, what do we do? If it is a valid node, we insert the left and the right child into our queue again. But if at any given point I see that my found is equals to true, that means I've already found a null node, and my wherever I am at, the new node is not a null node, then we return a false. And what do we mean by that? This is a statement that I'm trying to explain you. That means I've already found a null, and after null, I'm finding a valid node, which is not completely fine for this complete binary tree question. So that is where we return a false. And if we never find a false statement, we just return true at the end of the day. So this is the whole code. And if you want the code, it will be linked in the description as well. And if you